Thank you again for joining us. Uh, Whenever you are ready, please start your presentation, please.
Thank you. Thank you for the nice and kind introduction. And I'm Sungwon Yoon from Ulsan National Institute of Science and Technology, UNIST. And actually, I'm affiliated with Graduate School of AI and also in Electrical Engineering Department. So for today, I'm very glad to share our recent research works to you guys. And today's title is Understanding Model Flatness Across Running Frameworks. Actually, when you see the title, you can focus some keywords here. Model flatness is important keyword for understanding today's talk. And actually, our focus is finding some theory across running frameworks. When you try to understand running frameworks, we have variety of running frameworks for deep learning era. For example, when you try to train your model to minimize the loss with a ground truth label, then we can say this kind of framework is supervised learning. And you can think of unsupervised learning. And actually, when you think of a generative model, actually generative training is quite different with a conventional supervised uh, cross-entropy loss, actually. And when you think of reinforcement learning builds another branch of running frameworks. And so when you try to think of and imagine the contents of today's lecture, I want to build a theory for understanding model flatness across reinforcement learning or generative models, etc. So let's get started today's lecture. So introduction, I want to share the basic concepts of loss landscape in deep models. And actually, it is a long-aged problem for understanding the loss landscape in deep models. And actually, researchers have some insights and understanding for for a certain cases deep learning. However, for another various kinds of running frameworks, we have a very lack of understanding. We do not have any theory to understand the loss landscape of the reinforcement learning on generative models. And so I want to share our group's research works. Actually, two works are recently published in ICCV and ICLR, and their focuses are on generative training and reinforcement learning. So I want to share our series about understanding loss landscape in deep generative training and deep reinforcement learning and conclusions. So let's go ahead. So this is a preliminaries and introduction. So we can think of loss landscape of a model. So when you, for example, when you have a model with millions of parameters, actually for current large language models or large foundational models contains almost billion, more than billion parameters. And however, for very popular resonance structure, we have a millions of parameters. And by the way. And actually, we have a bunch of parameters. And when you try to think of, actually, it is large dimensional visualization. So it is hard to understand in our 3D world because human has a 3D vision perspective. So we cannot understand higher order of dimensions. However, when you try to think of the loss values across parameters, and you can think of these kind of here, this kind of something landscape on it, right? Actually, it is hard to visualize with 3D illustrations. However, when you can imagine, right? And some position on some point with a good parameter position, then you will see very minimized loss values. However, when you are not in the optimal position, then you will see large values, right? So we can have these kind of varying shapes of the loss values across model parameter axis, right? So when you try to visualize it 3D, actually it is not a correct one. However, it is for a conceptual visualization. And your deep learning training is to find a good minima, right? So you traverse around the loss landscape here, and you are going to find some good minima when you try to repetitive training of your models by thanks to the stochastic gradient descent, right? So training is to find the value with the minimal loss values. And actually, when you think of the exact shape that you have when you are in the minima, we can separate two types of minima. First one is flat minima, and another one is sharp minima. And it means literally when you are in the flat minima, your loss landscape around the minima is very smoothly varying. So for example, when you are here, when you assume you are here, and you have a very smooth shape around it, right? So you can say it is a kind of flat minima. However, when you are in the very sharp here, for example, then you will see very rapidly changing loss values around you, right? So we can think of these kind of shape of loss landscape. And actually, for classification, for example, and actually it contains a broad concept of supervised setting for minimizing the loss. And for this case, the shape of the loss landscape and its role and its understanding, theoretical understanding is well documented. For example, when you are here, flat minima, and you can locate here, sharp minima, and their difference is that flat minima is enhanced model robustness than the sharper minima. So when you try to understand how this kind of gain is achieved, for example, here, black colored plot indicates your train loss shape. And when you calculate your train data loss values and when you illustrate your plots of the loss values, then let's assume that we have these kind of things. And actually, in this flat minima version and sharper minima version shows a similar comparable loss values. So we cannot see some differences when you try to calculate the loss values for the train data because they are good enough. However, when you test or evaluate your models to another setting with different types of data, for example, t-test, then actually, unfortunately, your loss landscape will be slightly different with train data distribution. So here, when you have these kind of slight shift or changes of test distribution loss values, then when you are in the flat minimum, then you will see a very slight degradation of your model. However, when you are in the sharper minimum, then you will see some very dramatic performance degradation because of a very slight perturbation or variation of the loss values. So this kind of conceptual illustration says that when you find flatter minima, then you will get some model robustness against shift of data distribution from train to test. So it is very quite important thing because when you try to evaluate your model within a task, even within a task, you split train and test distribution, right? Actually, their underlying distribution formula is the same. However, you have to build test and train split with disjoint sample selection. So you can say that your loss landscape will be slightly different from the train and test. And for example, when you think of dramatic shifting from train to test, for example, when you think of corruption robustness of your model or adversarial robustness, or you can see so many domain shift or domain generalization issue, then for these kind of any shifting cases, actually flat minima shows some meaningful gains. So that's the understanding of the flat minima of the supervised settings. So this kind of flat minima is quite easy to find. For example, when you try to find flatter minima, you have to use this kind of flatness term when you try to optimize your models. So here you are at the weight W. However, when you consider just only one minima value here, then actually it just consider the actual loss values at the exact position. However, when you add some perturbation on the model weight. And when you see some difference between before perturbation and perturbation, if you are at the flatter minima, then actually their difference should be minimized. So when you encounter these kind of terms, and overall when you train to your models, then actually your model goes to the flatter minima rather than sharper minima. So it is very easy but explicit way to find flatter minima, and it is called SAM, actually sharpness aware minimization. So it's very widely known method to find flatter minima. It is very easy. It is model agnostic and task agnostic. And for another methodology, you can find flatter minima by using weight averaging. So stochastic weight averaging is when you pick your models on your training trajectory, and when you're taking an average of that models, and it is called stochastic weight averaging. And it is widely known that stochastic weight averaging shows or yields a flatter minima solution. So when you try to use this kind of thing, you can also find flatter minima rather than sharper minima. And these kind of technologies or methodologies can have a gain or various kinds of tasks. And this picture illustration comes from the newspaper 2021. And it is not our work, but it is a very popular work that showing the advantages of the flatter minima in domain generalization. So authors here, this paper tries to uh, make a tune of weight averaging with a dense version. So it is called SWAD, dense. And by using this, they show some meaningful gains for domain generalization. And when you try to and when I try to give details of the domain generalization setting, you can shift your images from art painting domain to cartoon or photo on sketch, and you have to measure the performance on the unseen domain. So you run dog and cat images on art painting, and you can test your models to other domains. So when you do this kind of thing, this kind of flatter minimal really indeed shows a value. So when you try to wrap up this introduction part, so advantages of flat minima are well documented in supervised training and classification, distributed optimization, or domain generalization, and also corruption robustness and adversarial robustness. You can see some meaningful gains by finding flatter minima. So how about actually modern deep learning era has very different training architectures and training frameworks. For example, generative model or reinforcement learning, and they are very essential running framework in modern era, right? So how about this kind of running frameworks? Can you naively just extend the flat minima understanding to generative model or reinforcement learning? And actually, it is not, because generative modeling is quite different with just minimizing the loss. Actually, we try to model prior distribution. So your model is trained to output generative distribution itself. It is kind of mapping to the input. So actually, their setting is not the same as supervised training. Just supervised training is you take the input and you just try to map the input to a certain loss value. However, generative modeling does not, right? And reinforcement learning is quite more different, because reinforcement learning is a kind of uh, time cascaded process to maximize reinforcement reward. So it is not a ground truth, or it is not a supervised matching problem. So it is hard to understand what's the effect and roles of the flatter minima in reinforcement learning also. So based on it, I want to introduce two recent works of our research group. And first one is generative training perspective, and for the second one is reinforcement learning perspective. So let's start from generative training perspective, and it is published in ICCV 2025. And it's this work read by two wonderful students. And this is a collaboration research with Professor Jae-jin Yu in the same affiliation. So our table title is Understanding Flatness in Generative Models and its role and benefits. And so my key question is, does flat generative models produce the same image when the various inputs are given? So when you try to think of model flatness for generative models, when you try to think of diffusion model, we have a parameterized denoising module. And the parameterized module can have some flat minima, right? And if so, then what is the effect? So when we think of the flat minima role in supervised loss minimization, then for that case, we can map the perturbed version of inputs to the same loss. It means that when you have a clean image, then you have a very minimized loss. And even you have a adversarial perturbed input or corrupted input, then your model should have also minimized loss, right? This kind of concept let us think of flat model maps the different inputs with the same semantics to a certain loss values, minimized loss values. And that's the key essence of the flat models in supervised learning. When you try to extend this kind of understanding to generative models, it is quite not identical to each other because flat generative model, then if we sample some noise from the sampling, and when you try to map this noising sample to the real data distribution, then if your model map your different samples to the identical generated sample, then it is not a benefit, right? Because your model should mimic the overall distribution of the train, and you have to show diverse generated images to better FID, right? So it is not the case. So let's try to understand how it works for the flat generative models. So actually our paper focuses on the diffusion model. So this is the basics of diffusion. And diffusion models, for the brief understanding, I guess that you guys already know the basics of the diffusion models. So diffusion models is a kind of denoising and noising trajectory. So when you have a clean data, and forward means you can add more noise step by step. So when you repeatedly add noise, then actually this clean image goes to undistinguishable, just a Gaussian noise distribution, right? And when you go backwards by finding this kind of solution, and this kind of backward can be called as denoising. And when you try to parameterize this kind of denoising module, then you can repeatedly denoise your noise samples to the clean image. And you can add some conditioning to guide this kind of noising process. So when you try to think of this kind of process, the diffusion model is a stochastic. This diffusion model is iterative process of denoising, right? So this is basic. So let's try to understand the role of the flatness in the generalization, the generative models. And we try to address this kind of question with two theorems in our paper. And our key question is like this. What is the meaning of the perturbed model in the distribution? It means that for flat model, if you perturb your parameter values, you will see consistent loss value, right? And what is the role and what is the effect of the perturbation of your model parameters in your generative model distribution? And second question is, how this kind of effect leads to some kind of robustness. Actually, I did not precisely specify robustness for the generative models. However, just imagine some robustness will come out from these kind of perturbed or flat minima. So how this kind of robustness will be, right? So let's go ahead. So our key theorem is the first theorem. So we try to interpret the perturbation of the model parameters for the generative models into the prior distribution that models try to learn or try to generate. So Px is the original prior distribution of the given x. So your model is proposed to run or parameterize the run to output the Px, right? This kind of process. And we are trying to interpret or translate the perturbation of the theta into the effect of the target distribution. I will say Px is a target distribution to be generated by your models. So when you add some perturbation in here, and let's say that we have a perturbation with delta here. So delta perturb minimum. So you will shift to your model on parameter space with delta, and delta is constrained with a sphere with a large delta. And if you have a delta, then it translates into some versions of target distribution. So I will give you an exact formula here. So when you have a delta, and actually we have something kind of function. Actually, I'm not giving the details of it, and details are in the paper. And so we have a something function, an exponential value. So it can be called as some kind of scaling. So your target distribution is given, and your target distribution becomes scaled, right? So this kind of perturbation in the parameter space will lead to some scaling of your target distribution. And when we think of all the possible perturbations within this sphere, then you will see a bunch of varieties of scaled target distribution, right? So when you try to minimize your generative model's loss values, for all perturbed model parameters, then it directly links to your model shows minimized loss values to generate this kind of multiple variety of scaled target distribution. And also non-scaled PX. It also includes non-XPX, and we have scaled distribution. So it is kind of minimizing loss for the set of distribution, not just a single distribution, but your model tries to minimize loss value, generative loss values for the set of scaled distributions. So that's the effect that is understood by our theorem. And so what does the perturbation model represent in the distribution? So model perturbation is translated to perturbed distribution. Actually, it is a scaled version of priors, and resulting in a model being trained on a variety of distributions. And then we hope to link this kind of concept to robustness vector. So let's assume that we have a delta flat minima. So we assume that we have a flat minima. And actually, when we have a epsilon distribution gap robustness, so our series like that. So when you find some distribution here, per parameter perturbation within delta, within large delta, and we have all zero force loss for the parameter versions, and it links to all the zero forced values or loss values for the scaled distribution. And when you measure the largely or maximally perturbed version of scaled distribution, then we can measure the diverse on it, right? So we have it, we can take a diverse Pn scaled P hat here. And when you take the max value, and we know that our generalization robustness of the flat minima will be less than the maximum divergence that we have in the scaled set. So it means that we can have a robustness against data distribution shift P to P hat and the largest value that we can meet, we can use here is d max here. So it means that we can achieve epsilon distribution gap robustness. It means that when you change slightly to your target distribution, then your generative models can build or can generate the shifted version of distribution. So it is kind of generalization issue of generative models. And actually, generalization issue of generative models is not well documented because generative models always focus on generating a target distribution. And distribution shift is, I don't know. So actually, this kind of theorem is, to my understanding, is to first attempt to theoretical understand of the distribution gap robustness of the generative models. So we can link the flatness to distribution gap. So as the model has the flatter minima, the model is robust to generate all the possible perturbed distribution within the gap here. So that's the key core parts of our theory. And we try to empirically validate our theory. We utilize explicit method that I already introduced to you guys, SAM, sharpness aware minimization. And we add sharpness aware minimization to generative models, and we can utilize another various kinds of implicit methods, stochastic weight averaging, and actually EMA is widely known as a powerful tool for getting a good generative models. So we have EMA and a bunch of things. So by doing so, we can clearly see the gains here. So ADM is the baseline diffusion models. And baseline diffusion models, and we have a T20, T100 means the test inference steps. So when you have a small steps of denoising, then you will see larger FIDs, worse FID. And when you go through more steps to denoise, then you will get a very lower FID than the T20 case. And we have three different benchmarks here. And we have SAM, and we'll add various kind of methods. For example, EMA, SWA, and IP is input perturbation. And we conjecture that this kind of algorithms all consistently pointing to the flatter minima. And when you add SAM, actually their performance is very good. And when you add more, another versions of algorithms, methodologies, EMA or SWA, we can minimize FID very well. So this kind of research show that when you try to find flat minima, your generative model will be improved. So that's the good signs of our research. And actually, for another perspective, we try to understand the robustness of your model against quantization. So when you have applications to deploy your models, then you have to care about the computing resource. So you have to quantize your model. And we conjecture that sharpness aware minimization or flat minima have a very strong robustness against quantization, because quantization can be understood as a kind of perturbing your model parameters, because you drop the raw precision, less important, less significant precision of your model, and you try to map your model parameters to incorrect but similar values with a lower bit quantization. So this kind of process is kind of adding noise or adding quantization error to your model. And when you are at the flatter minima, you guys all know, we all know that parameter perturbation has a minimal effect for the flat minima, right? So when you try to use more quantization levels, then SAM does not hurt its performance. So it has a consistent performance. However, baseline shows very large performance degradation. So this is another advantageous perspective of flat minima of generative models. And this is a quantization qualitative illustration, and you can see clear advantages of it. And this is the flat minima quantification. So you can measure the loss increase along the norm of the perturbation. So when you add more perturbation, your loss should be increased because you are diverging from it, the solution. So however, when you run your model with the SAM, your SAM shows very flatter behavior around the perturbed region. So we can have a very good flat metric here. So LPF is a flat metric. And so we have a very raw values. It means we are located in the very flat loss landscape, actually. And so for another perspective, it is very important perspective. So diffusion models, when you try to test your diffusion model by sampling test distribution, and actually key problem is exposure bias because diffusion process is iterative process for denoising. So step-by-step process always have a suffers from cascaded error. So when you go further, then your error will be amplified. And lastly, you will at the another position is a kind of cascaded error propagation. And exposure bias is a error propagation problem that happened in your diffusion models in testing. So when you are training your diffusion models, you will have a very good, nice trajectory for denoising. However, when you test your models, then this kind of strategy will be diverge from the training trajectory because it is test sample. So trajectory with error accumulation is exposure bias. And we conjecture that flat minima have a strength for minimizing this exposure bias. So this is a illustration of the results. So we have a training curve here is a time step, and we have error variance here. And when you see another baselines and baselines have different error values because they have a differently diverge from the training trajectory and their error will be increased or variance will be increased. However, SAM is the most close to the train trajectory. So it means SAM will have a minimized exposure bias. So this is another important perspective for flat generative models. So that's the all the parts for this chapter 1. And we know that we can build robust generative models by finding flat minima. And we also provide some series to understand the roles and benefits of the flat minima in generative models. So let's go ahead. So let's slightly tune our attention to reinforcement learning. So reinforcement learning, as I said, it is kind of aggregated optimization across time steps, rewards. And then actually it is not the case of the supervised learning because we don't have any ground truth policy, but we try to just maximize with open problem, right? So flat reward, we try to understand the meaning of flat reward in policy parameter space because a widely used deep reinforcement learning tries to run the policy with parameterized functions. So we try to understand when we have a flat reward in policy parameter space, then what is the effect? And actually, when I try to say the results and conclusions, it implies robust reinforcement learning against various kinds of perturbations. So this work is published in ICLR and ICLR, and it is selected as an oral presentation. So this is a reinforcement learning framework. We all of you guys know about it, right? We have to learn deep policy by interacting or communicating with environments, and environments will return reward or state transition with MDP, predefined MDP, and your deep policy tries to optimize your actions to maximize the return, accumulated return. However, when you think of robust scenario, we have some changes from train to test. So these kind of changes can be diverse because in supervised running or classification, we can just imagine some perturbations in input distribution. However, for reinforcement learning framework, we have a bunch of different factors, right? We have action, we have a reward, and we have a state transition. So when you think of some erroneous cases for all the factors, we can have some noise in actions. It means that when you try to control your robots and your robots have some imperfection of your hardware, so your action have some noise. That's a kind of possible scenario, right? And when you think of environment case, environment will return rewards. However, in reality, you have to measure the reward value actually. However, this kind of measuring can be done with sensors in your robots or systems. And this kind of reward values can be diverse, right? Have some noise and it can be incorrect. So we can think of some errors in rewards and also state observation. State observation should be done with a sensor data, right? So it can be erroneous, right? So when we have these kind of erroneous setting or shifting of the distribution, then we have a failed policy for that case. For example, here we have a humanoid-like robot control in Mujoko environment. And when we have no perturbation, this robot is dancing and walking very well. However, when we have a slight changes in environment, for example, roll friction or big head, a roll friction can be understood a kind of state transition becomes slightly different, and big head means your also state is becomes differentiated training distribution. And when you have this kind of diverse setting or erroneous setting or perturbed settings, then your policy that looks seemingly very good at training will fail to have a good policy in test setting. So this is a robust reinforcement learning, and it is quite a challenging problem in reinforcement learning society. So in this perspective, we try to understand reward flatness. So actually, reward is a factor to be maximized. So we have to see reverse direction because we do not have any ability, but we have a something kind of flat too. For example, with a very flat region of the high space, right? So we have a flat reward here like this, and flat reward means that we have a consistent high reward values across parameter perturbation, and when you perturb a lot, then it starts to degrade. And when you have a sharp flat rear, then it means that you have a good performance at this position. However, when you perturb your parameters slightly, then it dramatically degrades. This policy fails a lot. So we can imagine this kind of definition of flat reared. And let's go ahead. So flat reared can be understood this kind of scenario. So we have a epsilon, and within epsilon, let's assume that we have the same expected cumulative reward, and it means the definition of the reward flatness. And so before going to the details of the method of mass, we think of, we imagine how the flat behavior uh, leads to the behavior of your agents. So we prepared a preliminary experiment to understand robustness of your policy. So let's start from this position, and your goal is to navigate to the goal position. And it is a very naive and simple scenario, right? It's just a very simple 2D navigation problem. And actually, we have a very quick trick here. So we have a obstacles, blocks, the paths. However, we have a very slight slip paths that your agent can going through to the goal position. So when you try to solve this kind of problem with reinforcement learning, the easiest trajectory or easiest policy is just going ahead, right? Go upward direction. An easy task, if you go only goes up, then you can go to the goal position very easily, quickly. However, this kind of policy have a very sensitive to the mistakes, your actions. For example, when you choose to go left or go right, when you are going through this kind of very narrow path, then you will meet some obstacles here, right? And you will fail to find the goal position. So this kind of scenario does not allow a very slight mistake in your actions. But if you don't have a slight mistakes and you can if you can guarantee a perfect choice of your actions, then you can go ahead and you can quickly maximize the reward values. So this this scenario is what we done. So so we train our model with traditional RL, PPO, just proximal policy optimization. And when you train your models, you always find some trajectory straight to the goal position. And it means that it is the easiest way, and your training always proposing to go directly to the goal position. And this kind of policy can be done because in training scenario, we do not have any action robustness or action perturbation, right? We can control our musical or simulation results without errors, right? So your policy always select to go upward, to go to the goal position. However, we train our RL or PPO by adding sharpness aware minimization to find flat reward solution. And we do not care about paths, or we do not have any explicit tuning and adaptation in your paths. We do not care about the policy, but we just try to find flat reward or PPO. And when you find flat PPO, then it eventually goes to this kind of detouring of the obstacles to the goal position. It does not select the go straight forward direction, but it go around to detour the obstacles to the goal position. And this kind of scenario means when you go around here, then if you have some action errors, it does not hurt the reward, right? Because we have some gap, we have some distance to the obstacles, so we can guarantee a very good reward. Even with a perturbation of the actions or any other errors or perturbations. So this preliminary results show that by just using flat reward, it links to robust decisions and policies in the specific problem. And we do not explicitly utilize this problem setting and problem structure and policy and actions, but we just simply care about the flatness of the reward. And it directly links to the robustness of your policies. So that's the key message. And actually, it is almost all the essential messages of our work. So, in theory, let's try to understand theoretically. So we always try to do this kind of scenario with math like this. So we have a P and we have a uncertainty set. It means that we have some uncertain action and uncertain perturbation of the states with the distribution, with a stochastic distribution. It is not a deterministic way. And when you have this kind of thing, and our goal is to links this uncertainty with flat reward, right? So I think it is better to go to the direction here. So we will define epsilon flat reward maxima, and as I already mentioned, we have a flat reason of the reward here. So we have a epsilon perturbation, but we can keep your rear very high value. And there's a parameter space. And when you translate the parameter space perturbation into action or action domain, then we can have an action perturbation. So we have action A deterministic without error, and we have a stochastic behavior to adding the noise to the action. Then we have some perturbation of actions. So this is a perturbed version of actions is the possible outputs of your models to considering stochasticity of your policy. And our goal is when you have this kind of flat reared, it links to the action robustness. So key proposition is given here. So when you have a epsilon flat reared maxima, then it leads to some certain quantity action robust policy. So it means when you have a flat reared, then you can guarantee some robustness against action perturbations. So this is a simple formula given here. And actually, I think we can go further to show the empirical results is up to 48. So let's go ahead. So we have a bunch of tasks, Muzuko tasks. We have Chira and Hofer and Worker. And we have a baseline comparison with PPO and conventional robust training of RL. And actually, RNAC and RARL always tries to utilize some action space and input space, try to make your policy to be robust. It is not a viewpoint from policy landscape. So this is a result. We have a SAMPPO, so please focus on the orange colored plot here. So we have a bunch of baselines, and when you add more noise, actually your training is not done with noise. Your training done with a clean setting, and you're trying to add noise in your testing only. So when you add more noise, then your models kept considerably better performance than baseline. Actually, it is hard to defend the decrease of reviewers across all the noise factors. However, you have a very slight noise, slowly decreasing behavior. However, other factors and other RL robust reinforcement learning shows a worse performance than ours. And when you add action to Hopper, Worker, we have a consistent gains across all the environments. And we have done more things when you have some variations in state. For example, actually state is not covered theoretically in our paper. However, we empirically test how this affects links to the state transition probability perturbation or other things. So when you have a changes in mass and friction of your Mujoku environment, your testing is done in the 1.0, and when you have a perturbation, you can clearly see that orange colored policy always generally locates the top position when you compare to the baselines. So it means your model, your flat reared links to very robust performance across various kind of divergence. So when you graphically illustrate mass vector friction, most of them in a one picture, then yellow colored reason means high reared. So we have a much broader reason of high reared positions for SEM plus PPO. So that's it. And we also tested with reared perturbation, adding Gaussian noise when training. And when you try to add some noise, your SEM plus PPO shows a very high performance than others. So that's all the results, experimental results for RL training. And you can visualize the leeward surface, and your SAM-PPO shows much flatter region of the high leeward region. And then flatness measure also shows very minimized values, and it means that you actually find the flat surface. So that's it. So this is conclusions for today's lecture. So we established a theoretical understanding of flat models in generative tasks and reinforcement learning. And actually, before our works, flat behavior of the loss landscape is well documented and well analyzed in supervised training framework. However, a recent goal of our research group is to expand this kind of theory into diverse running frameworks, including generative models and reinforcement learning. And we expand it and we provide some theory for different running frameworks, and we figure out what is the advantageous robustness for each running frameworks. And our theory explains loads of benefits. And loss landscape perspective is not a direct augmenting of data distribution, thus exhibiting better scalability property. So I will say more details about it. So when you utilize a flat aware optimizer, and your cost is just adding one more gradient, because when you try to find flat region, you have to calculate gradient one more time. So it means that your computing resource requires approximately 2 times more computation resource than simple stochastic gradient descent. However, most important case is that we can detour the scalability issue in input domain. It means that when you try to make your robust models naively, just seeing the data distribution, you have to prepare wide range of data distribution. You have to prepare corrupted version of your data and adversarially perturbed data and your domain shifting data and variety of data bearing perspectives, and include all of them. Your data set will be very extensive and large, heavy, and heavy training on this kind of just increasing scalability issue with data always gives some problems. When you try to train your models, you have to care about number of batches, right? You will going through much more epochs and iterations to your train with a wide range of data distribution. So before this kind of flat perspective, you always try to think of this kind of input scaling. However, when you find flat solution, even in generative models and reinforcement learning, you can directly guarantee the robustness without expanding your data distribution. Just doing one more gradient. It is not a costly. So our work has revealed that. And actually beyond these works, we are trying to expand our viewpoints to the data perspective also. So our recent work has revealed that data augmentation, which is kind of expanding data distribution more broadly, and data augmentation techniques actually leads to flatter solution, and it unifying our previous series or generative models and reinforcement learning into data parameter duality. So it means that when you expand your data, it leads to the flatter solution. And when you try to find flatter solution, actually it translates to the effect of seeing diverse virtual data. So it means they have some duality from data and parameter perspective. And actually this work is accepted to AAAI for the next year. So it is not included in this talk, but I hope to introduce this kind of work is done by our group. So lastly, I want to introduce our nice and wonderful team, because these works are done with these guys. So our group is Machine Intelligence and Information Theory Lab. And actually, I studied a lot about information theory when I was a PhD student. And after that, I changed my focus to AI and running theory and try to understand the running paradigm by seeing the information theory and maths. So our research always focus on tackling this kind of direction. So we try to find some generalization issue, robustness issue, and try to understanding series of it. And for some kind of distributed and decentralized optimization process in multimodal cases. And actually, by using this kind of foundational knowledge, we try to expand our knowledge to AIX problem and AI plus communication and network problems. And communication and network problems is very long-aged problem of information theory. So I want to expand our AI knowledge to communication and network society. So this is our wonderful students in our group. So that's it for my presentation. Thank you for your attention.
So thank you very much for the presentation, Professor Yoon. It was truly insightful, and we really appreciate the clear explanation of the model flatness across different learning frameworks. So now, are there any questions from students? So please feel free to ask the question on Zoom chat.
I think we have some questions in chat. So, first of all, thank you for the excellent lecture. Thank you. Among the various types of uncertainty, such as action perturbation, transition variation, reward noise, which factor had the greatest impact on the flatness effect? Actually, frankly speaking, our theory just tried to link model flatness and action perturbation. Actually, our math does not include transition variation or reward noise. So when you try to anticipate the effect of the action perturbation and transition variation reward noise, my guess is that transition variation will be very effective or impactful when you see some side effects of the perturbation. When you think of transition variation is a kind of changing the MDP structures, right? So we try to change the transition probability itself. So you transition, so your models will face up to with very dramatically changed transitions, even with the same action and even with the same state. So I think that the effect of the transition variation is much more higher than the other factors. And reward noise can be diminished because when you have a noise, but when you have a accumulated version of reward, then your Gaussian noise can be zero forced because plus Gaussian noise going to the unbiased estimator of your mean value, right? So reward can be solved like this. However, transition variation will be very impactful in your model robustness. So next question is, you show that flatness helps generative models handle gaps between training and testing data, right? In wireless, we often need to simulate signals under different noise conditions. Could flatness allow us to train a single generative model that works well across many different noise levels, including having to train a separate model for each one? All right, this is a good position because good question. Because when you think of some perturbation of your parameters, when you translate into input domain, it goes to some kind of in capturing boundaries of perturbation in the input domain, right? And we do not have to care about what types of noise that happens in your clean data, right? When you are in the encapsulable region of your input domain, then we can guarantee zero force data. So I guess that flatness might effective to solve your problem with noise agnostic something systems. So for another question, flatness tended to improve robustness, but I'm wondering whether obtaining flatter minima typically increase training time or computation in overhead. Right. So computation overhead, we have to calculate one more gradient for each iteration. So it makes your computation resource 2 times more than the naive stochastic gradient. However, training time, I feel that it is not a theoretical intuition, but I feel that we do not have to care about, we do not need more rapidly more or largely more training time for that because training time can be increased because of 2 times gradient in computation. However, when I see some iteration numbers to be used for training for finding a flat minima, it is not much increased. So I guess that to answer your question, your training time approximately can be 2 times larger than the naive one, because we have to compute gradient 2 times. However, uh, actually, it is a gradient. Counting gradient is not the core part, not the most of the part of your computation. Because when you are learning your models, you have to think of time latency for memory uses and computing other values and forward process or other things. So these kind of extra uh, inference time or training time does not double for SEM. So it is not it up to the 2 times more computation time, but I guess that it is slightly less than the 2 times. So, next question is, as model size increases, billion plus parameters, does the benefit of flatness scale, or does it diminish due to loss landscape geometry changing in high dimensions? This is a very important question. So when you think of capacity, your model, actually when we have a large models or large number of parameters, then it means we have large capacity to train, right? And when you have a large capacity, and when you train your large models with a very scales data, it means that sparse data, it means that data distribution is not wide and task is very easy, but you are trying to use very large models, then your model will find some very sharper minima. However, when you add SAM, but it goes to this flat minima. So it does this kind of effect does not diminish. However, when you try to think of an issue, we have to think of issue. When we have a large models, then we have over parameterized capacity, right? It means that we have some parameters that does not affect the task a lot, but it seems like a meaningless or redundant parameters. When you think of large language models, large models, not all the parameters are have a clear objective. They have a very small, some almost all values are very small, and it looks very enough in does not have any effects on the loss values. However, this kind of over-parameterized factor actually links to the flatness because it does not, they are the factors or parameters does not affect the loss value. It means that to that direction of that factors of parameters, you can keep your loss values very flat. So over-parameterization can be linked to better flatness, actually. So we have a two factor. We have a large capacity, and you have to care about some overfitting, right? You can have an overfit in your model to the very sharp minima. However, when you try to utilize your parameters very well with the regularized versions of loss or something like that, then you can go to much flatter reason than the shallow model. So next question. Thank you for the great lecture. Thank you. And I have question if the law of flatness versus invariance and approaches like data augmentation or equivalent architectures try to build invariance explicitly, while methods like SAM directly optimize for flatness in parameter space. In the long run, which direction do you seem as more fundamental for achieving robustness and generalization? Uh, when you try to think of again for the last comment that I give you, uh, I believe that data invariance can be linked to the model flatness in parameter distribution, parameter surface. So we proved the duality for the input and parameter space in to be published in Triple AI 2026. However, when you try to select more fundamental way to find flatter minima, I believe that SAM will be the fundamental one because SAM tries to explicitly use surface behavior of your loss landscape into your objective function. So it have a very direct and explicit tool or way to regularize your training to the flat model, flat reason. So I think it is more fundamental. However, when you utilize good data augmentations or any invariance uh, tools or methodologies, and they can be linked to the flat minima. So final one, in wireless communication field, great wireless communication. We often work with the signals that come from diverse and changing channel conditions, which can be seen as some different data distributions or noise. Could this flatness principle be leveraged to train a single robust generative model that can synthesize or analyze signals effectively across a wide range of conditions? Great question. So to answer this question, I think it is better to go to our group introduction page here. So for here, actually, we are also researching on the communication, AI plus communication, and our WALMAM paper is a conference, is a prestigious conference for communications and actually, our work is about AI-based blind signal recognition. And actually, when you think of blind signal recognition, your wireless signals can have a variety of modulations and phase or something like that, right? However, when you try to use AI, you can classify your signal into correct modulation, even without sharing the protocols or underlying facts of the another RAN. So for that case, actually in our evaluation study, we add stochastic weight averaging based flat minima searching methodology to AI-based blind recognition. And for that, we have some meaningful gains to recognize variety of wireless signals. So I think that your suggestion is valid suggestion, and flat minima may help to recognize AI-based wireless system to handle variety of signal divergence. So that's it. So I think all the questions on chat are done. I'm not sure my answer is great, but
Thank you, Professor. So,
thank you.
all right. So, thank you for the our question, and once again, thank you for the Professor Yoon. Thank you so much for your time and for the talk today. We sincerely appreciate your effort, and this concludes today's seminar. So, thank you everyone for joining. 네, 교수님
Okay.
감사합니다.
네, 감사합니다. 저 초청해 주셔서 감사합니다. Thank you for inviting me and have a nice day. Thank you.
네, 감사합니다.
예.
नाम का फोल्डर अभी तक इसके मिस हो रहा है और आप यहाँ पर देखो कि ये प्लान बना रहा है पूरा इसे टेक्निकल आर्किटेक्चर डॉक्यूमेंट बनाया फिर इसके बाद ये कोड लिखेगा फिर इसके बाद ये बताएगा कि कौन सा एंड पॉइंट क्या करेगा कैसे करेगा मुझे इसकी थिंकिंग एबिलिटी और एआई कितना अकेले अचीव कर पा रहा है ये चीज बहुत ज्यादा इंटरेस्टिंग थी मैं यहाँ पर प्लस पर क्लिक करके ब्राउजर भी खोल सकता हूँ और अभी तक कोई भी डिफरेंट से बाद भी आप देखो ब्राउजर में खोल सकता हूँ हम लोग वेट करते हैं इसके बन जाने का एंड ये स्टेप बाय स्टेप